independent voltage source. What's an independent voltage source? Now, the way we draw that when we designing that, we draw it looking like this. It's a circle, and we put a plus and minus on it. So this might be something like this. Plus, minus, 2 volts. That's an independent voltage source. That means that voltage is always going to be 2 volts. Doesn't matter when you look at it, doesn't matter what time of day, doesn't matter how much current going through it. The voltage here is going to be 2 volts all the time. It's always going to supply 2 volts. Normal battery, when you use them all the time, they get weaker. They go from 1.5 volt to what? Sometimes 1.3 volts, 1.2 volts, and suddenly 0.8 volts. Then it doesn't work because it's too low. These always stay 2 volts. The value of them is always the same. It doesn't depend on anything. It's always 2 volts. We have something called dependent voltage sources. We'll talk about them shortly. A lot of times, actually, if the source is an AC source, we'll graph it looking like this for an AC source. That's a DC. Direct current, DC, constant value. If it's an AC source, we have that squiggly line. So that source might say 2 sine 377t. So it's not a 2 volt, it's a sine wave with a peak value of 2. An AC source. So we put that squiggly line in it. If it's a battery, a lot of times the battery, we draw the battery like this. And we treat that as an independent source with the constant value, say 1.5 volt. So these are the symbols that we use for independent voltage source. Now, independent current source,
what did you say the last one was used for?
like a battery. Yep. An independent current source, again, independent always going to have a circle and an arrow either going up or down. It might say like 2 amps, 3 amps for that. So you might see me draw a circle like this and we have a current going up of 2 amps. You might see me design a circuit that has 3 amps going up and maybe another source of 2 amps coming down. There's 2 independent sources. This one's pushing 3 amps up in that direction. This one's pushing 2 amps in that direction. The net result of these, this is actually equivalent to 1 amp pushing upward. The net result, 3 up, 2 down. If you remember from last class, these are connected in parallel, right? When they're in parallel, they have what? Same voltage. The voltage across them is the same, but the current can be different. What you want to try to avoid there, this is a no-no for independent current source, is you don't want to draw something like this. You go, that's 3 amps. Put some element here, could be anything here. Then you put another current source here of 2 amps. That's a no-no. Can't be. Why? Because this one says, I'm going to push 3 amps up this way all the time. If that 3 amp enters that element, that means that 3 amp is going to leave that element. Current's not going to leak. If 3 amps going through this one says, I'm going to push in this direction 2 amps. What happened to the 1 amp, the difference between them? Where did it go? Can't. So that's why you can't connect current sources in series. So can't be. when they are connected in series like this one, what do we know about that when they're in the series? They must have what? The same current. Now, there are sources that depends on something. It's called dependent sources. So their value is not 3 amps. Their value might say 5 times the current somewhere else, 5 times the voltage somewhere else. So let's look at dependent sources. We'll look at dependent current source. And we use the diamond shape for a dependent current source. With the arrow there. So now I might have this circuit. This is an independent source, 2 amps. I'm not telling you what this element is. I have some element here. I have another element here. Number 1, number 2. I have another element here, number 3. And I have a dependent current source here. And I can make the value of that dependent current source depend either on current or on voltage. It depends on the design I have, what I'm using for instruments there, or devices. So for example, if I call this voltage Vx, I can make the value of this current source 3 times Vx. It is a current source, but the value of that is 3 times whatever the voltage right here. That's known as voltage controlled current source. It's controlled by the voltage. It is a current source. So this is actually a dependent voltage controlled current source. It's controlled by the voltage. Now, sometimes you have the same thing as you see above it. I have some element here. When I say element, could be another voltage source, current source, resistor, different things we didn't discuss. Could be an op amp, could be anything. I might have a current source like this, and the value of this current source, it might say 5 times the current I sub x. And I sub x, I might define I sub x as this current coming down. So this is also a current source, dependent current source. But now the value of this depends on what? On the current through this one. So that's a current-controlled current source. It's a dependent current source, and the value of this depends on the current through that. And that changes. For example, if I put a bigger source here, this current will be bigger, which means that source will be bigger. The 2 amp, always 2 amp. It doesn't change. It doesn't matter where you attach there. But this one, it depends on where I attach here. Like I can go and put a 5 amp source here. It does not change this one. I can put a 10 amp source here. It does not change this. This does not depend on anything, where this one depends on that current, and that current will be determined by this and other stuff in the circuit. So it's not a DC value, it's not a fixed value. This value changes, it depends what I put there. We also have dependent voltage sources. Let's look at dependent voltage sources. And again, dependent voltage source, just like the current source, except we'll have plus minus in it. And it could be that you can change the direction of it, the plus on the bottom, the minus on the top, doesn't make any difference. That's a dependent voltage source. So I could have a circuit that looks like this. 3 volts going through an element here. Maybe a current source here. 4 amps. Another element here. And a voltage source right there. And I can say this voltage, it's 5 times, I don't know, I sub x. And I can define I sub x as this current going in. It's a voltage source that depends on what? It's controlled by what? The current through that. So that's current controlled voltage source. So this source here, this dependent source, dependent voltage source, is current controlled. The value of this is controlled by the current coming through this. Or I might have the same thing. And I might say, you know what, what's this? Let's call this voltage here plus to minus Vx. And I want this voltage to be 7 times Vx. Again, that's a dependent voltage source. This dependent source is controlled by what? By the voltage. So it's voltage controlled. Voltage source. So that's what a dependent source looks like. So what's a dependent source? Anyone ever seen one? What do they look like? Take you back to physics. Anyone took physics too? Did you guys took physics too?
Capacitor?
Did you cover capacitors? How about two coils next to each other? When you have two coils next to each other, transformers. You know, the value of that transformer depends. You'll find there's a relationship between the current of the first one, the current of the second one, the voltage, the same thing. It depends how far from each other. You put them close to each other, far away from each other, the value will be changing. It depends on the value of the other one, how far you put them, because the mutual inductance will change. So these are dependent sources, you know. Let's take a circuit, put some stuff in it, and apply some of the stuff we learned between this class and last class. Let me just pick an example. Maybe I can find something. Back to the book. Come on, come on. Give me something. I don't know, I'll make some numbers up. Let me take a circuit. I'll make one up. Here we go. We have this. Hopefully I do a good job with it. No mistakes in it. 5 amp current source. It's in parallel with another element. I don't know what the value of that element is. There's another element right here. Let me label some voltages here. Let's say this voltage is plus to minus 4 volts. Let me label this current here 2 amps. Minus to plus the voltage here, 7 volts. That's a 7. Let's put another element here. This is plus to minus 11 volts. Let's put a dependent source here. It's a current dependent source. By the way, while I'm at it, let's look at this current, the 5 amps. I'll come back with numbers here. That 5 amps is going to come to this junction, is going to split. If you get 2 amps going this direction, what do you have coming down?
3.
Has to be 3. 3 amp coming down. This voltage here is 11 volts. Why 11? I shouldn't have given you that. Why is that 11? I just said 11 volts. Why? How is this connected? They're in parallel. They must have the same voltage. Just like these two are connected how? In parallel. So what's the voltage here? 4 volts, right? Now let's put some current here. What do you want that current to be? Let's define this voltage here. Minus to plus V. And this voltage is what? This is going to be a current source pointing down. And the value of that, let's say it's what? Pick a number. 1V, 2V, what do you want it to be?
6V.
6V. Okay. 6 times V. Can we figure out what this current coming down now? Going through this? Well, what is 6 times V? What is V equal to when you look at this?
11.6. Right? Or no,
What's V here? 7 volts, right? Minus to plus, the same direction. That's 7 volts. So what's 6 times 7?
42.
So there's really 42 amps coming down here. You have a 2 amps going this way. That means there has to be a current going up to make the 42 here. And how big that current will have to be? 40 amps. 40 and the 2 is 42. It comes down this way. So I couldn't just put numbers, crazy numbers. I had really to do all the calculation in my head to make sure these numbers are working. And the question, let's find the power absorbed or supplied by each one. Now you're going to find that we have conservation of power, meaning all the power absorbed should equal all the power supplied. Let's look at this source, the power by the 5 amp source. You have a current going up. That means that current is entering from which end? The bottom. If it's going up, that means coming from the bottom, going up. It's entering the minus or the plus. So that's a negative power. When the positive current enters the negative terminal, that's a negative power. 5 times 4, which is what? Negative 20. 20 means negative means supplied. So that means 20 watts supplied. That's what the negative means. Let's get to this one. We have 3 amps coming down here entering the plus. Let's label these 1, 2, and 3. How's that, so we know which one we're talking about? The power through element 1. I meant 2 actually, 2. This one here. So we have positive current entering what? Positive or negative? Positive. That's a positive here. 3 times 4, which is positive 12. That means 12 watts, what? Absorbed? Let's look at 1, right here. We get positive current entering what? The positive or the negative? Negative. The negative, that's a supplied. Negative 2 times 7, which is what? Negative 14, that's 14 watts supplied. Let's look at the 3 here. The current is going up. That means it was coming from where? It's coming from the bottom. We get 40 amps entering from the bottom. Entering the plus or the minus? Minus, so that's a negative 40 times 11. Negative, is that 44 or 440? That means 440 watts, what? Supplied. And the last one is the dependent source here. We got the current coming down. That's the dependent source. The current coming down, that's entering the plus, that's observed as 6 times 11. 40 times 11, not 6. What is it, 42? 42. I say, wait, we way off. 42, the current's 42. It's 6V, which is 42. Oh, this is done. Hey, 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 hey. Oh. 42 times 11, which is positive what? 452? 62. So that's 462 what? Observe. Let's see the total now. So observe. And total supply. If I made the problem correctly, that should be the same number. What do we have the total observed here? What do we have? 462 plus 12, right? 462 plus 12, 474. Supplied, what do we have? 20, 14, and 4, 40, right? That's a 4, 2 and 1, 3 and 4, 7, 474. Is that equal? Conservation. Still true. So if the problem is done correctly, the power supplied should equal the power absorbed. I think the last topic here in this chapter is resistors and Ohm's law. Let's talk about resistors. That's an S, it looks like a G. Now in the lab, if you look at the resistor, they look something like this. You probably were there in the lab looking at them. There's a wire coming out of each end. All the resistor looks like this. And some of them have like band 3 colors here, like this, and 1 here. Some have 4 and 1 there. And you probably learned in the lab when you were looking at the code, you look at each one, that gives you the first digit. The second one gives you what? The second digit. And the third one gives you what? Multiplier. And this one is what? Tolerance. So it's based on the color there, the code of it. If the first digit was a 1 and the second digit was a 7, when you look at the chart there, and the multiplier was 1,000, you go times 1,000. So the value of that resistor is what? 1,000 here. The value of that resistor is 17,000, or we go 17 mega ohms. Capital M. I mean kilo ohms. Sorry, not mega, kilo. 17 kilo ohms. Kilo is 1,000. Now, the tolerance is the percentage. It could be 5%, 10%, or 15%. Depends on the color of it.
Isn't there 20? Yeah.
Is that 20%? Yeah. The gold is the best one. That's usually within 5%. So when you look at the gold, if you have a gold banner here, or ribbon here, one stripe of gold, that means your value is going to be within plus or minus 5%. So your value of the resistor is only going to be off by the maximum is 5%. So that means it's going to be accurate by about 95% to 105. So that resistor should be between, what's 95% of that number? 17,000 times 0.95. Should be between 16,150 all the way to what? 5% above that number. And it's 17,850. So that's the minimum value of that resistor, that's the maximum value of the resistor. Should be between that. So when you pull one, it says 17K, you're probably not going to get a 17K. And it's funny, some of these resistors are exactly the same size. You pull one, it says 20 ohms. You pull the next one, it says 5K ohms. You pull the next one, it's 7 mega ohms. How can it be different if it's the same size? Because the value of the resistor depends on 3 things. Rho, that's a constant resistivity, times the length of the resistor divided by the cross-section area. If I had my physics book from last semester, we have a chart in it. It shows you what rho is, resistivity. What's on the inside of it. If it's germanium silicon, the value of that resistor is very small. If it's glass, rubber, the value of that resistor is high. Those are high values. Times the length of it divided by the cross-section area. So really the length, most of them have the same length, the same area, but this what we control is this piece, rho. What do we put on the inside of them? And if you break them, you'll see some of them have glass, some have little dust plastic in them there. Some have germanium, silicon. Yeah. But that's the value of R. The symbol for a resistor in our book is this one. When you see that, that's a resistor. So I might draw a resistor. So I got this resistor of 20 ohms. That little symbol is ohm. So 20 ohms. The value of this resistor, 6 kilo ohms. The value of this resistor, 11 mega ohms. Again, it's controlled by resistivity rho times L divided by the area. Most of them, L and A, are really the same thing. Not much of a difference in length or area. Might be a bit smaller, some of them, but the key one that controls that is rho. Yeah. So now we know what a resistor is. Let's look at Ohm's law. That's where we use the letter ohm here, or the term ohm. Ohm's law. Ohm's law says, in English, the voltage across conducting material is directly proportional to the current through it. Flowing through the material. If you remember from math, when something is directly proportional, what does that mean?
As one goes up, the other goes up, and vice versa.
Correctly. When one increases, the other one increases. So here it says the voltage across, the voltage is directly proportional. In math you say K times, I don't know if you remember that, K times the other value, which is the current, I. Well, we found out that K here happens to be the resistor. And that's what Ohm's law is, V equals Ri. The voltage is directly proportional to the current. By how much? By the value of R. So if I have a resistor here of 20 ohms, and I have a current source supplying current in that direction of 2 amps. That current is going to come down through that resistor. Assume there's other elements here. Maybe there's an element here. That current is going to come down traveling this way. There's the only current in the circuit is this one. So that means I have a current entering, traveling in this direction of 2 amps. And as current enters the resistor, it will mark it plus to minus. I said last time, current is like water. If you pour water on the ground, water is going to go from the high hills to where? To the low side. It's not going to go from the bottom up. It never climbs. Water is going to go from the top to the bottom. So as you go through that resistor, it's going to mark it plus to minus. So here the voltage, according to Ohm's law, equals the current, which is what? 2 amps, times the resistor, which is what? 20 ohms. And the voltage is always measured in what? Volts. 2 times 20, which is what? 40 volts. Now, if I take the same current source now, not the same resistor, but increase the current source to 4 amps, put a different current source. And I put a different current source now. That means the current coming this way now is 4 amps. And again, it's going to mark that resistor plus to minus. So the voltage here is going to be the current, which is the 4 amps, times the resistor, which is what? 20 ohms. And what do we have? 80 volts. Notice what? Oh, yep. As the current doubled, went from 2 to 4, what happens to the voltage? Also doubled. If the current here becomes half of that, guess what the voltage here becomes? Half of that number. It is directly proportional to the current. If this current increases by 2, this voltage will increase by 2. If this current decreases by 1, this voltage will decrease by 1. Or half, I mean. If you take actually like a nickel or a dime and measure the resistance to it, that's metal. Metal is a good conductor, so the resistance for that, the value for that is going to be very small. That's why when you see guys working on power line, what do they wear? Ever seen them? Electricians work on the power line? Look at their hands, look at their feet. They always have rubber gloves on their hand when they work on the power line. Why? Rubber is an insulator. Current's not going to go through it. So they can grab the wires, twist the wires, and connect them. Where they might have problem, now if that wire suddenly puts a hole in the glove, and that glove poke you in the finger, now we got a problem. But the other side of it is you need direct path for the current to go to the ground. So even if it touches your finger, it wants to go through your body, your skin, a lot of water in it. Water is a good conductor. Now it gets to your feet. What are you wearing?
Boots.
Rubber boots. It doesn't go through there with the boots there. Some of the commercials says, if you work on your yard, please call Dig Safe. And they'll tell you, even wooden ladder could conduct electricity. Wooden is very good. Wood is a good insulator. Does not conduct electricity. Unless it's what? Wet. If it's raining outside, saturated with water. So you have to be careful with that. But metal is a great conductor. So rarely you see somebody like working on power line with ladders, unless they're protected with actually the ladder itself has a big piece of rubber on the bottom or the top, the hands. There's lots of, because the wooden ladders are heavy to put them on these power line. They'll snap them, So if you look at most screwdrivers that you have when you're working on these, the end of it is actually rubber or plastic. They even cover the metal with plastic so you don't make contact. Because we know rubber is a good insulator. And that's the same thing almost for heat too. If you poke in a fire with a metal rod and you keep poking that fire, next thing you're burning your hand. So most actually fireplace equipment at the end, they have a piece of wood at the end because wood is an insulator. Cooking pans, the same thing. So now let's look at that Ohm's law. So this is Ohm's law, V equals IR. Probably the biggest law in electricity. It's a short one, but we use it all the time. V equals I times R, or R times I. That's Ohm's law. Almost the first law of electricity, almost. Now, we know power is equal voltage times current, right? It's either supply or absorb. That's what we did. But let's add to that Ohm's law. Which says V equals I times R. So if I go to power now, in place of V, let me put I times R. That's what V equal to. And multiply it by I. Power becomes what? I squared times R. Now, looking at that equation, Ohm's law, you can solve for I. I equals what? Isn't that V over R? So if you go back to power, power equals V times I. And you take I out and replace it with what? V over R, using Ohm's law. Power becomes what? V squared over R. So 3 ways to calculate power. Power could be V times I, if you know both of these. If you only know the current and the resistor, you can use I squared times R. If you only know the voltage and the resistor, it's V squared over R. R is the resistor. By the way, we call it resistor why? Because it's supposed to do what? Resist the current. Block the, bless you, block the current. So the bigger the resistor, the more blockage you're going to have. Small current is going to go through it. The smaller the resistor, the what? The larger current going to go through it. It resists current. I mentioned earlier that to calculate the resistor, I said resistor R is equal to what? Rho times L over A. Just for the sake of discussion, let's say we have L equals 1 centimeter, which is 0.01 meters. And the area is, I don't know, 0.0001 meter squared. Assume that's the case. Small area. Actually, that's not really small, because that's equivalent to 1 centimeter by 1 centimeter, right? The cross section, that's a big resistor. So we're talking about a resistor like the size of this cab. You know, that's not really small. That's a big wire. That number, 0.001, isn't that 100 over 100 when you multiply them? 100th times 100, that's 1 centimeter by 1 centimeter. So it's something 1 centimeter by 1 centimeter that way. That's how big that cable is. That's a heavy-duty cable. That's not a small cable. So let's modify that. So we're talking about a cable, I might be able to see it better actually, the size of this. You know, so let's add a couple more zeros here to make it really small, because I'm saying meter squared here. Make it small. And let's say I use for that, inside of it is copper. I fill the inside, or the wire made out of copper. What is R for that? For copper, I'm looking here, our book has a few of them, has a list. It has a resistivity of, I'll show you that number, 1.7654. Copper, 1.7654. Micro. What's a micro? 10 to the minus 6, right? So this will be 1.7654 times 10 to the negative 6 divided, times L, which is what? 0.01 over m squared. Well, if I move the decimal point, that's 1, 2, 3, 4, 5, 6. 1 times 10 to the negative 6. These two are the same. I can cancel them out. So the value of that is probably 0.018 ohm, roughly. small resistor. We said copper is a good conductor. All they're giving us actually here is metal. Metal, all of it's good conductor. If I use aluminum instead of copper, switch that, the same problem now, to aluminum. And aluminum for that, rho is 8.4805 times 10 to the negative 6. So the value of that resistor will be 8.4805 times 10 to the negative 6 times 0.01 over 1 times 10 to the negative 6. And that's 0.085 ohms. Still a small value, but this is about 5-6 times bigger than that. So the current through that, because that's about 5 times bigger than this, will be about 1/5 of that current. They don't give us anything for rubber and plastic, and do we have anything? So here's the problem. Where we encounter a problem in real life is wiring in the house. The Basketball Hall of Fame, I think I remember somebody says 21 miles of cables. These cables are going to work like resistors. They're copper. The length is 21 miles. So we have to deal with these cables, with these wires. So a lot of times we neglect, oh, who cares about the wire? Oh, no, we got to deal with these wires. So when you actually buy wires, they come in different gauges here. 2, 4, 6, 12, 14, 18, 22, 24, 28. And if you know each one, you know the cross-section area. And that tells you how many ohms per 1,000 feet of cable. So if you get the skinny wires, that's the 28 gauge here. Notice this really thin wire. They have 65 ohms every 1,000 feet. If you get the 2 gauge wire, the cross-section area is, oh, this is millimeter, by the way, not meter, millimeter squared. 33.6, they have that many ohms per 1,000 feet. So when we buy these cables, we have to pay attention. Like for example, they're doing 24 miles here. If it's 24 miles, you got to calculate how many centimeters long that cable is. And this particular one happens to be 520 microohms. It's not a big one in the micro. That's 3.9 times 10 to the 6. The cable diameter is 2.5, was 2.5. What kind of a cable here? Do they tell us what kind of a cable? This example. Two islands here. They're not telling us what 2 islands. The distance between 24 miles. The voltage is 500,000 volts. And maximum capacity of the system is 600 megawatts. Calculate the maximum DC current flow and estimate the resistivity of the cable. Well, if we know actually, first we have to go through it and calculate what we have there. We know the maximum is what? 600 megawatts. Or 600 times 10 to the 6 watts, right? Can you see that? The voltage, it says the voltage is going to be what? Is that 500,000 volts? Ohm's law, V equals, or power equals what? Voltage times current. Power equals voltage times current. We know what the power is, that's the power. We know what the voltage, can you calculate the current? 1200 amps. That's the maximum that island can have. So if all these homes exceed 1200, we got a problem. We have a switch to flip. It says, okay, you're done. Because now you're going to burn that wire there. So now let's calculate what the resistor of the wire we're going to be attaching or sending there. So the wire is 24 miles long. Let's calculate the length of it. Roughly 3.9 times 10 to the 6 centimeters. The resistivity, now they're solving the problem backward. What is the resistivity of the wire there? This is the resistivity. We know what the resistance is. With the cable diameter to be 2.5 centimeter, the cross section is 4.9 centimeters squared, pi r squared. That's how they came up with that number. Pi r squared. Diameter is 2.5, the radius half of that. So pi r squared is that number. So that's the area. Calculate we know what the length of the cable. We know what the resistance of that 417, it says in the problem. Somewhere they're going to have 417 ohms. Where was that listed in the problem? Somewhere here. So we can calculate what the resistivity rho is. Again, they're going back to this equation backward. If you look at the equation, it looks like it's backward to where I wrote. Because if you have R equals rho times L over A. If you multiply both sides by A, you have R times A equals rho times L. So what is rho equal to? R times A over L. And that's the equation that they're using to calculate rho for that example. They're saying we know R is going to be, what was it? They want it to be 417. They're giving us the cross-section area, which is pi r squared, divided by the length of the cable. And the length of that cable was 3.9 times 10 to the 6, 24 miles. We know what R is, so we can calculate what rho is for that cable they're using. And we can select the right cable for that. If the maximum resistance 417, it says, well, rho has to be 520 micro ohms for this calculation. You might say, well, how do we know what this value is? How do we know the 417? Well, they told us what the maximum power is, right? Power, they said the maximum power for us is what for that problem? 600 megawatts. That's 600 times 10 to the 6. And in the problem, they told us the maximum voltage. Maximum voltage is 500 kilovolts. 500 times 10 to the 3 volts. Power equals voltage times current. Power, 6 times 10 to the what? 8. Voltage, it's 5 times 10 to the what, 5th, is it? Times the current I. What's I equal to? 6 EE to the 8 divided by 5 EE to the what? 5? 1200 amps.
You gotta move over a little bit.
Ohm's law says what? V equals I times R. We know the voltage. 500 times 10 to the 3 equals the current 1200 times the resistor R. So the maximum resistor you can have for that cable, we can calculate that, even if they didn't give us that. Divided by 1200. They don't have to give us the value of R, we can calculate it. 417 ohms. That's the maximum resistor you can have for that cable. So now we can select what kind of cable to use. That over that distance, because know what they come in the standard, like how many ohms per 1,000 feet. I need the maximum to be this number. So let's see which one I'm going to use. I can calculate what rho is. This is rho. So if you know that, you can work the problem backward, and you can figure out what rho for that cable should be, and you can figure out, okay, what material to use. Okay, we are done with this chapter. Just a little introduction to different things.